So good morning, everybody. I'm going to talk about the recently started new experiment with the concurrent electrical stimulation functional MRI in human. So the connectivity is important. So as Brodmann said, that one can never justify any separate specially differentiated psychic centers within its whole. So, for example, like two intracranial contacts, we deliver the stimulus, and even though there is no stimulus observed in two of these contacts, there might be still some synchronization going on, like phase synchronization. So the network-based neuroscience is important. So try to understand the brain function that causes certain behavior or percept from the standpoint of the brain's long-range interactions. So that's what we are going to do. So methods to study brain connectivity, this anatomical connectivity by the fiber tracing, dye, or isotope injection is great. And then there are a lot of good literature using the non-human primate. So this is great, but in human, it's very difficult to apply this method directly in living humans. And also, we don't know how there is a connection, but how this connectivity is functioning during the human behavior. So this is same as DTI method. And people also use functional MRI to probe the connectivity using resting state, for example. But this also lacks the causal components. Basically, this is time series correlation, so there is no causality inferred. And also, we can do resting state ECOG. This is also problematic sometimes because of the limited spatial coverage. And we are also doing this intracranial cortical evoked potential. So we put the grids here and grids here, and they stimulate one contact electrically, and then record the evoked potential from other grid electrodes. And this is we can sometimes clearly show the focal response in this grid. But also this lacks the spatial coverage. So hopefully we want to know the whole brain connectivity from one site. So that's why we combine these two methods, which is concurrent electrical stimulation and functional MRI. We call this ES-fMRI. So our subject is our 8 patients with the intracranial intractable epilepsy who needed long-term invasive monitoring. So this is just a picture of during the operation. So we opened the dura very widely and put these grids and strips and depth electrodes into the patient brain. So this is post-op MRI, post-op CT, and post-op X-ray. And this is the patient like this. And this patient was monitored chronically for approximately 1 to 3 weeks in the specially designed epilepsy monitoring units. And we implanted this specially designed electrodes. This is macro-micro hybrid contacts. But this basically very similar to the DBS, clinically used DBS electrodes. So we have macro contacts here. And then these small contacts are micro wires so that we can record single unit from these contacts. And also we also implant this 96 high-density grid electrodes. And then after monitoring period, epileptologists decide the treatment plan. And after this treatment plan was determined, the patient was brought to the MRI room, and then we did the ES-fMRI experiment. Currently, we are using 3T Siemens Skyra scanner. And so this is a schedule of the patient. So pre-implantation MRI, we usually do pre-implantation MRI session. So this includes the structural scan, a functional scan, and the resting scan. Like this is the resting scan of this patient. And then after 1 or 2 weeks, electrodes were implanted. And then post-op day 1, we confirm the electrode position by doing this structural scan, CT and MRI. And then this 1 to 3 weeks period, patients were monitored chronically, 24 hours, 7 days a week. And then during that period, we can do a lot of experiment on the patient. For example, this is a response from 1 microwires in the Jesus gels. And then this is 0 is the start of the tone onset, tone stimulus. And then so we can know that this contact is responding to tones, like this. Then we can determine, let's stimulate this contact. Then 1 day before electrode removal, the stimulation-functional MRI session is held. Then also we are following up this patient like 4 to 6 weeks after the operation. And then post-op follow-up MRI session is done. This includes also structural scan and functional scan and the resting state scan. So we can examine how for example, the resection of the mesial temporal lobe changed the resting state scan between this time period. So doing this experiment on the patient, the safety assessment is very important. So the most important thing is the radiofrequency pulse-induced heating of the electrodes. Then this International Electrotechnical Commission guideline, the implant's temperature could not exceed 38 degrees. So that means that we have a temperature increase. Temperature increase should not be more than 1 degrees. So we measure. We use this phantom, gel phantom, PAA phantom. We created this phantom, and then using RF transmit head coil, and then put the fiber optic temperature sensor here attached to the electrodes here, and then do scanning. This fiber optic temperature sensors measure the time constant of decaying fluorescent light strength. Depends on the, so this time constant is very depending on the temperatures. So these MP range, gradient echo EPI, the fast spin echoes, these are most commonly used MRI sequences. And the MP range is just 180 degrees inversion pulse, followed by very small degrees of flip angle. So this can be a very low. And then the gradient echo EPI is 90 degrees typically, and followed by very fast gradient switching. The fast spin echo, the 90 degrees excitation, followed by many 180 degrees flip angle. So the induced heating depends on the number of RF excitation, the flip angle, square of the flip angle. So we can expect that the fast spin echo is much more dangerous. And so this is one of the results of temperature measurement. So this x-axis is time, and the y-axis is temperature increase. And this is 1 degrees, this is 0. So this is red line indicates that duration, period of scanning. So MP range, typically very low temperature increase. So this is approximately 0.6 degrees increase, but typically very low. And also gradient echo EPI we are using for the functional scanning. It's also temperature increases definitely less than 1 degrees in this our experience. But if you use fast spin echo, the temperature increase is much more larger. This is 1.5 degrees, so which exceeds the limit. And also we examine using the body coil RF transmission with the GEEPI sequences. And this also, as expected, sometimes this temperature increase exceeds 1 degrees. So we have to be very, very careful using body coil. And this temperature change is very dependent on the orientation of the phantom or electrodes. So we implanted, we placed the lot of electrodes in the phantom. So this is 23 contacts temporal pole grid, skull-based 32 contacts grid, and 20 contact depth electrodes, and frontal 32 contacts grid, like this orientation. And we rotated this phantom, like 0 degrees, 90 degrees, 180 degrees. And then this is a temperature measurement. X-axis is time, y-axis is temperature increase in Celsius. So as you can see, this temperature heating, effect of heating is very depending on the orientation. And it's kind of unpredictable, very, very depending on the temperature orientation. And also sometimes exceeds 1 degrees. By the way, this is using the spin echo sequences. Oops. And then we observed one incidence using fast spin echo with a transmit-receive head coil. We observed this 5 degrees, more than 5 degrees heating, like this. So it's very dangerous to use fast spin echo or turbo spin echo sequences, even though in this case we don't have the blood flow, so which is a very strong heat exchange mechanisms. But we did not, this never used with fast spin echo sequence cannot be used with intracranial electrodes. But gradient echo EPI or MP range could be done with small and acceptable risk on the patient. And the other thing is that electrode movement. So if you, there is a current flow inside a strong magnetic field, there is a force generated by this magnetic field. So we videotaped the movement of an electrode inside the scanner during the stimulation session, and with various waveform. This is biphasic waveform, and this is monophasic waveform. And then this x-axis is pulse width. The y-axis is the repetition rate from 50 hertz, 100 hertz, 150, and 200 hertz. The pulse width started from 0.2 millisecond to 2 millisecond to 2 millisecond. Then the red dot shows we observed apparent movement inside the scanner, inside the phantom. So looking at this, the monophasic waveform, as you expect, it's kind of dangerous. The electrode movement, there is a force, apparent force to the electrodes. So we are just using biphasic waveform with 0.25 millisecond pulse width at 100 hertz. Like here, we are here. And this is the setup and the design of the experiment. So digitized stimulus waveform is generated by the computer, and then this goes to the stimulus isolators. We used two stimulus isolators in parallel to boost the the current. And then this is connected electrically to the scanner room here. But we put some RF radio frequency filter on the patch panel between control room and the scanner room to prevent the noise contamination. And the scan sequence is usual gradient echo planar imaging. And then we put delay in TR, short delay in TR, like 100 milliseconds, so that we can deliver stimulus when the scanner is off, or there is no RF or gradient switching. So the stimulus is delivered only at this time period. Okay. So constant current biphasic, we are using constant current biphasic stimulus square wave pulse. Well, we are using 9 to 12 milliamps, 100 hertz, and then 5 to 7 pulses. So just the stimulation period is 50 milliseconds to 70 milliseconds. And this is one of the example of the amygdala stimulation response. This is a stimulation site, and then this is the response. The notable is we observe the expected region of the response, like medial frontal lobe, orbital frontal cortex, cingulate, and then this posterior cingulate cortex. And then also this is STS. So the notable is that we observed a lot of negative response, so that this method can be used the quality of the connectivity is not always just the positive side. There is a negative both response here. So we can skip this. So the summary, so concurrent electrode stimulation functional MRI is a promising method for studying whole brain causal connectivity in human brain. And under our specific condition and setup, concurrent electrode stimulation of intracranial electrodes and functional MRI can be performed with small acceptable additional risk to the patient. And each institute should perform safety tests under its specific setup and equipment. And these are our collaborators. This is Dr. Howard, Matt Howard, who is leading this laboratory. And I appreciate this Louis Remy and David Kamikar for very valuable assistance in terms of conducting a safety test. Ralph Adolphs, Tim Griffith, Ms. Magnota, our MRI physicist, Chris Peterkoff, who is doing a lot of ES-fMRI in monkeys, and Hiroto Kawasaki, who is doing epilepsy surgery, and Anton Kruger, who is also the engineers, our engineers. Thank you very much for your attention.